What if I told you there's a scientifically valid way to travel faster than light without breaking Einstein's laws? A method where you don't move at all, but space itself carries you across the galaxy in days instead of centuries. It's called the Alcubierre Drive, and it's not science fiction. It's real physics, published in peer-reviewed journals, debated by the world's leading scientists. But here's the twist. This incredible technology comes with a dark secret. 6 massive problems stand between us and the stars. Problems so severe that one of them literally turns the warp drive into a time machine, threatening to unravel the fabric of reality itself. Some obstacles might be solvable with advanced engineering. Others might prove the universe has absolute limits we simply cannot cross. By the end of this journey, you'll understand why faster-than-light travel might be humanity's greatest dream or its most impossible fantasy. If these cosmic journeys fascinate you every night, don't forget to subscribe to our channel and like the video, because you will find more on this channel every night. Ready? Then let's begin. Part 1. Introduction and Fundamentals of the Alcubierre Drive. Miguel Alcubierre's 1994 discovery and Einstein's field equations. Back in 1994, a physicist named Miguel Alcubierre asked himself a question that would change theoretical physics forever. Could the fictional faster-than-light warp drive from Star Trek actually exist in the real world of general relativity? It wasn't just idle daydreaming. Alcubierre took Einstein's field equations and did something nobody had quite done before. He flipped the script entirely. Here's how physics normally works. You take a bunch of masses and energies, describe how they're distributed using something called the stress-energy tensor on one side of the equation, and then you calculate how space-time curves on the other side. Cause and effect. Mass creates curvature. Simple enough, right? But Alcubierre reversed this entire process. He started with a specific geometric structure, a warp bubble, if you will, and then worked backward to figure out what kind of masses and energies would be needed to create it. Think about that for a second. Instead of asking what space-time looks like around a star, he asked what kind of exotic configuration of matter would be needed to create a specific space-time shape. It's like designing a building and then figuring out what materials could actually support it, rather than starting with bricks and seeing what you can build. This backwards approach was audacious, unconventional, and it opened up a whole new way of thinking about faster-than-light travel. His solution became immortalized as the Alcubierre Drive, spawning dozens of follow-up papers and endless debates. Now, calling it a drive is a bit misleading. There's no actual blueprint for a spaceship here, no instruction manual for building one in your garage. A better name might have been the Alcubierre solution or the Alcubierre field, but the name stuck. And honestly, it sounds way cooler than it has any right to. What makes you think humanity could ever master something like this? The mathematics work, at least on paper. But mathematics and physical reality don't always see eye to eye. We're about to dive deep into whether this concept could ever escape the realm of theory and become something real. Stay with me, because the journey gets wild. Warp bubble geometry and operating principle. So how does this thing actually work? Picture a bubble moving through space. Inside that bubble sits a central region of completely ordinary, flat space-time where passengers would calmly reside. Nothing unusual happening there at all. No weird time dilation, no spaghettification, just regular physics as we know it. But here's where things get interesting. Behind this bubble, the fabric of space itself expands and pushes the passengers forward. It's remarkably similar to how our universe is currently expanding, driving galaxies apart from one another. The passengers inside can actually remain stationary relative to their local space-time, They're not moving at all from their perspective. Instead, the space they're sitting in is moving, carrying them along like an airport moving walkway. Imagine standing perfectly still on one of those conveyor belts at the airport. You're not walking, not running, just standing there while the belt carries you forward. The Alcubierre bubble works on the same principle, except instead of a motorized belt, it's space-time itself doing the heavy lifting. The bubble contracts space in front of the ship and expands it behind, creating a wave that surfs through the cosmos. This isn't science fiction technobabble. It's a legitimate solution to Einstein's equations. The geometry allows for faster-than-light travel without technically violating relativity. Why? Because the passengers aren't actually moving faster than light through their local spacetime. The spacetime itself is moving. It's a loophole, a cosmic cheat code that might just work, but here's what keeps physicists up at night. Creating this bubble requires warping spacetime in very specific ways. Not just a little bit, but dramatically. And warping spacetime requires energy and mass. Lots of it, more than you can possibly imagine. We'll get to those terrifying numbers soon enough. Can you imagine what it would feel like to sit inside such a bubble, knowing that space itself is flowing around you like water around a boat? The stars ahead would appear blue-shifted, compressed in frequency. The stars behind would redshift into darkness. You'd be riding a wave through the cosmos, untouched by the extreme velocities happening just beyond your protective shell. How to warp space? The ultra-thin shell structure. We already know that mass warps space. Arthur Eddington proved it back in 1919 when he observed starlight bending around the sun during a solar eclipse, confirming Einstein's predictions. The sun's massive gravitational field curves space-time around it, and light follows those curves. So if we want to create a warp bubble, we need mass. But not just any mass configuration will do. The Alcubierre solution requires a carefully engineered ultra-thin shell of material surrounding the bubble. Think of it like an eggshell, incredibly thin yet precisely structured. This shell has to distort space-time in exactly the right way around the ship while keeping space-time completely undisturbed, both inside the bubble and far away from it. It's a surgical precision warping of reality itself. Inside the bubble, passengers experience normal flat space-time. Outside, far from the bubble, space-time is also flat and undisturbed. But in that narrow shell region, space-time curves dramatically, creating the expansion behind and contraction ahead that generates the warp effect. The shell acts like a lens, bending space-time without affecting the regions it's supposed to protect. How thin are we talking? We're approaching the Planck length, the smallest measurable distance in the universe, at roughly 1.6 times 10 to the negative 35 meters. At this scale, space-time itself becomes a quantum foam where our known physics starts breaking down. Building anything at this scale is so far beyond our current technology that it makes building pyramids with stone tools look trivial by comparison. Yet physics doesn't explicitly forbid it. That's the glimmer of hope here. No law of nature says you absolutely cannot manipulate matter at the Planck scale. It's an engineering challenge, sure, but it's an engineering challenge of such staggering complexity that calling it impossible might actually be understating the difficulty. We're talking about technology that would make our most advanced particle accelerators look like stone hammers. What separates science fiction from science possibility? Often it's just a matter of engineering sophistication and available energy. The Alcubierre Drive sits in this strange territory where the math works. The physics allows it, but the practical requirements are so extreme they border on fantasy. The fundamental advantage: no speed limit for space itself. Here's the beautiful genius of this concept. Mass cannot accelerate past the speed of light. Einstein showed us that. As you approach light speed, your mass effectively increases toward infinity, requiring infinite energy to push you faster. It's a hard wall, an absolute cosmic speed limit for matter and energy. Nothing with mass can break it. But space itself has no such restriction. Space doesn't have mass. Space doesn't have energy in the conventional sense. Space is the stage upon which the cosmic play unfolds, and that stage can expand or contract at any rate it wants. We see this happening right now with the expansion of the universe. Distant galaxies are receding from us at speeds exceeding light speed, not because they're moving through space that fast, but because the space between us and them is expanding. The Alcubierre Drive exploits this loophole ruthlessly. The central region containing the passengers could theoretically travel at arbitrarily fast speeds because they're not actually moving through space faster than light. They're standing still in their local reference frame while space carries them forward. It's like the difference between swimming across a river versus standing on a boat that's being carried downstream. This means no time dilation for the passengers. No twin paradox where you return home to find everyone you knew has aged and died while you barely aged at all. You could traverse the galaxy and return to Earth having experienced the same passage of time as people who stayed behind. That's radically different from near light-speed travel where relativistic effects become significant. Imagine crossing 10 light-years in a matter of days or hours, not decades or centuries. You could visit Alpha Centauri, our nearest stellar neighbor, and be back for dinner. Well, maybe a late dinner. The possibilities are intoxicating. Interstellar commerce, exploration, colonizational, suddenly become feasible rather than multi-generational endeavors requiring colony ships and frozen embryos. But before we get drunk on possibilities, we need a serious reality check. And that reality check comes in the form of 6 major problems that stand between this elegant mathematical solution and anything resembling physical reality. Physical plausibility warning. Here's where we pump the brakes hard. Just because a solution exists mathematically doesn't mean it's actually physically plausible. General relativity is a powerful framework, but it allows for all sorts of exotic solutions that may have no physical realization in our universe. White holes, naked singularities, traversable wormholes, the equations permit them, but we've never seen them and may never see them. The Alcubierre Drive doesn't violate general relativity. That's important. Einstein's theory doesn't forbid this machine from existing. There's hope in that fact. But hope isn't the same as probability. The gulf between mathematically consistent and physically achievable can be vast, and in this case, it might be unbridgeable. This topic gets sensationalized constantly, especially on YouTube. Clickbait titles scream about warp drives being built in labs or NASA developing faster-than-light technology. The reality is far more sobering. Serious physicists recognize the Alcubierre Drive as a fascinating theoretical playground, not an engineering project waiting to happen. We're about to systematically examine 6 fundamental obstacles that stand in the way of making this dream real. Some might be solvable with sufficient technological advancement. Others appear to be fundamental barriers imposed by the nature of reality itself. The difference matters enormously. Energy requirements that dwarf the mass of the observable universe. The need for exotic matter with negative mass that may not exist. Control systems that seem physically impossible to implement. Radiation levels that would instantly vaporize anything nearby. Paradoxes that require one warp drive to build another. time travel causality violations that threaten the logical consistency of physics itself. These aren't minor technical hurdles. These are fundamental challenges that force us to confront the limits of what's possible in our universe. Whether those limits are hard boundaries or just extremely difficult engineering problems remains hotly debated. The honest answer: we don't know yet. And that uncertainty is both frustrating and thrilling. What would you sacrifice to touch the stars within a single human lifetime? That question drives us forward even when the obstacles seem insurmountable. The Alcubierre Drive represents humanity's audacious refusal to accept limits. Our determination to find loopholes in the cosmic rules, even if it never works. The journey of exploring it teaches us profound truths about space-time, energy, and the fundamental nature of reality. The next sections will test your understanding of physics and challenge your intuitions about what's possible. Some problems have partial solutions. Others remain completely unsolved. All of them are fascinating. Let's dive into the details and see just how deep this rabbit hole goes. Part 2: Energy and Matter Requirements. Problem 1: Excessive energy needs. Let's talk numbers. And when I say numbers, I mean numbers that will make your brain hurt. Shortly after Alcubierre published his paper, two physicists named Fenning and Ford decided to calculate exactly how much energy would be required to actually create this warp bubble. What they found was nothing short of absurd. Their estimate came out to roughly 10 orders of magnitude greater than the mass of the entire observable universe. Read that again. Not 10 times the mass of Earth. Not 10 times the mass of the Sun. 10 orders of magnitude beyond everything we can see in the cosmos. Every galaxy, every star, every planet, every atom of matter and energy in the observable universe multiplied by 10 billion. And you'd still need more. Think about what that means practically. You can't just mine asteroids or harvest solar energy for this project. You'd need to somehow harness energy equivalent to billions of universes. Where would you even get it? How would you store it? How would you direct it? These aren't engineering questions anymore. They're questions that transcend anything we understand about physics or reality. But here's where the story gets interesting. In 1997, just 3 years after Alcubierre's original paper, a physicist named Chris van den Broek had an idea. What if you could modify the shape of the warp bubble slightly? Not change the fundamental concept, just tweak the geometry a bit. He ran the calculations and discovered something remarkable. By adjusting the bubble's configuration, Van den Broek managed to reduce the energy requirement from 10 orders of magnitude beyond the observable universe down to just 3 solar masses, 3 suns worth of energy. Still ridiculous, absolutely. Still far beyond anything humanity could achieve. But the psychological impact was profound. Imagine reading those papers as a teenager, which is exactly what our narrator from the original research did. In just 3 years, pure human ingenuity had reduced the energy demand for a warp drive from 10 universes to 3 stars, from complete impossibility to merely staggering impossibility. That kind of progress inspires hope. It makes you wonder what further refinement and research might accomplish over decades or centuries. Could we get this down to 1 solar mass? To the mass of Jupiter? To something achievable with advanced fusion technology? The trajectory suggested that maybe, just maybe, continued theoretical work could bring the requirements into the realm of extreme engineering rather than pure fantasy. That's the power of scientific progress. Problems that seem insurmountable today become tractable tomorrow. But there's always a catch, isn't there? And this catch is a big one: the ultra-thin shell problem. Remember that ultra-thin shell of material we mentioned earlier? The one that needs to warp space-time in precisely the right way? Well, it turns out that ultra-thin might be the understatement of the millennium. We're talking about a shell approaching the Planck length in thickness. The Planck length is approximately 10 to the power of minus 34 meters. That's 1.6 times 10 to the negative 35 meters if you want to write it in scientific notation. It's thought to be the smallest measurable length in the universe. Below this scale, the concept of distance itself starts to break down. Space-time becomes a quantum foam, a seething mess of virtual particles popping in and out of existence, where the smooth fabric of general relativity dissolves into something far stranger. At the Planck scale, known physics simply doesn't work anymore. Quantum mechanics and general relativity, our two most successful theories, both start giving nonsensical answers. We need a theory of quantum gravity to understand what happens down there, and we don't have one yet. String theory, loop quantum gravity, and other candidates exist, but none are proven. So how are we supposed to engineer a structure at a scale where physics itself is uncertain? It's like being asked to build a bridge on ground that might not even exist. You can't manufacture something when you don't know what matter even means at that scale. You can't manipulate particles when particles might not be particles anymore. Does this kill the Alcubierre drive completely? Not necessarily. Physics doesn't explicitly prohibit structures at the Planck scale. It just means we have absolutely no idea how to create them, manipulate them, or even detect them. This is what physicists politely call an engineering challenge, though that phrase doesn't quite capture the reality. It's an engineering challenge of such mind-bending sophistication that it makes building the pyramids look like playing with toy blocks. It makes splitting the atom look like striking a match. It makes landing on the moon look like a pleasant afternoon stroll. We're talking about technology that would require a complete revolution in our understanding of matter, energy, space, and time itself. Yet stranger things have happened in the history of science. People once thought heavier than air flight was impossible. Nuclear energy was considered fantasy. Quantum computers were theoretical curiosities. What seems impossible today sometimes becomes routine tomorrow. The question is whether the Planck scale engineering represents a very hard problem or a fundamentally impossible one. We honestly don't know. Which side would you bet on? Human ingenuity overcoming absurd obstacles, or the universe having hard limits we simply cannot cross? Problem 2. Exotic matter and negative energy. Now we arrive at perhaps the most fundamental problem of all. Everything we've discussed so far assumed that you could actually gather the energy and mass needed for the warp bubble. But there's a tiny detail we haven't mentioned yet, that energy needs to be negative, as in less than zero, as in something that may not exist in our universe. This was recognized immediately in Alcubierre's original work. Creating the warp bubble doesn't just require lots of energy. It requires negative energy, which through Einstein's famous equation E equals mc squared means negative mass. And that's a problem because we've never seen anything with negative mass. Not once, not ever, not even a hint of it. In general relativity, there's a rule called the weak energy condition, or WEC for short. This rule states that all time-like observers must see positive energy density. What's a time-like observer? It's basically anyone moving forward through time, experiencing a normal flow of time. Like you and me and everything we've ever encountered. The weak energy condition says the universe doesn't allow negative energy densities for such observers. Violating this condition isn't just breaking a rule, It's challenging one of the foundational assumptions about how reality works. Alcubierre himself recognized this problem. In fact, 27 years after his original paper, he wrote his only follow-up paper specifically exploring this violation in greater detail. That tells you how serious the issue is. Negative energy or negative mass would be what physicists call exotic matter. The word exotic here is code for we've never seen it and aren't sure it exists. It's not antimatter, which is real and well understood. Antimatter has positive mass and positive energy. Exotic matter would be something far stranger, something that would repel rather than attract gravitationally. Is there any hope at all? Well, there's something called the Casimir effect that some warp drive optimists cling to like a lifeline. The Casimir effect is a well-documented quantum phenomenon where two very close metal plates experience an attractive force due to vacuum energy differences. The region between the plates has lower energy than the surrounding vacuum, creating what looks like negative energy pressure. Experiments have confirmed the Casimir effect exists. It's real physics, not speculation. So doesn't that give us the negative energy we need? Unfortunately, it's not quite that simple. The Casimir effect produces energy that's negative relative to the background vacuum energy. If you removed that vacuum energy, there'd be no negative pressure at all. It's unclear whether this relative negativity could be harnessed to warp spacetime in the way required. Still, it represents a glimmer of possibility. Maybe there's a way to manipulate vacuum energy on large scales. Maybe there are other quantum effects we haven't discovered yet that could produce the exotic matter needed. The universe has surprised us before with unexpected phenomena. Could it surprise us again? The 2021 studies and ongoing debate, just when it seemed like exotic matter was an insurmountable barrier, something interesting happened in 2021. 3 separate papers appeared in relatively quick succession, all challenging the conventional wisdom about the weak energy condition and warp drives. The timing might seem suspicious, but there's a mundane explanation. Remember 2021, COVID lockdowns, scientists stuck at home with time to think. The 3 papers came from Bobrick and Martiri Fell and Heisenberg and Eric Lentz. Lentz specifically mentioned in an interview that this was what he spent his lockdown working on. While everyone else was baking bread and watching Netflix, he was trying to solve faster-than-light travel. Different priorities, I suppose. Lentz's approach was particularly creative. Instead of using the linearized approach that Alcubierre had refined in 2017, Lentz split spacetime into many layers and used hyperbolic relations to model their rapidly evolving states. His solution looked quite different from the classic Alcubierre bubble. Instead of a simple sphere, he proposed diamond-shaped regions formed by layers of rings and disks. The material forming these structures would be super-dense fluids, similar to what you'd find in the interiors of neutron stars. Not exactly easy to work with, but at least it's positive energy matter. Real stuff, not exotic negative mass. If his solution worked, it would sidestep the entire exotic matter problem. That's huge. The excitement in the physics community was palpable. Maybe, just maybe, there was a way to create warp bubbles without violating fundamental energy conditions. Maybe negative energy wasn't required after all. Maybe faster-than-light travel was back on the menu. But then came the pushback. In 2023, Jessica Santiago and her colleagues published a rebuttal that threw cold water on the whole party. They argued that all 3 papers had made the same mistake. Sure, they'd found positive energy solutions for one particular choice of observer. But the weak energy condition doesn't just need to be satisfied for one observer. It needs to be satisfied for all time-like observers. When Santiago and her team examined the solutions more carefully, considering all possible observers rather than just one convenient choice, they found that all three proposals definitely violated the weak energy condition. Worse, they concluded that this violation is a generic feature of warp drives more broadly. Not just these specific solutions, but the entire concept seems to require exotic matter. Lentz disagreed with Santiago's rebuttal. The debate continues. Papers are written. Arguments are made. This is how science works, through proposal and criticism, claim and counterclaim, gradually converging on truth through vigorous debate. Where does this leave us? Honestly, it's controversial. The optimists point to the Casimir effect and argue that vacuum energy manipulation might provide a path forward. The pessimists argue that the weak energy condition violation is fundamental and unavoidable. Both sides have compelling arguments backed by serious mathematics. What's your intuition here? Does the universe allow negative energy or not? Is the Casimir effect a loophole we can exploit or a false hope? These questions remain unanswered, and that uncertainty is both frustrating and fascinating. The broader implications of exotic matter. Let's step back and consider what exotic matter would mean if it existed. We're not just talking about a new particle or a new form of energy. We're talking about something that would revolutionize our understanding of physics more fundamentally than the discovery of radioactivity or quantum mechanics. Matter with negative mass would fall upward in a gravitational field instead of downward. It would accelerate away from regular matter rather than toward it. If you pushed on it, it would move toward you rather than away. It violates every intuition we have about how physical objects behave. The laws of motion we teach in introductory physics would need asterisks and footnotes. Could such a thing exist without us having noticed it? That seems unlikely. Negative mass would interact with regular matter in very obvious ways. We should see its effects in astronomical observations, in particle physics experiments, in everyday phenomena. The fact that we see nothing suggests it's either extremely rare or simply doesn't exist. Yet quantum field theory, our best description of particles and forces, doesn't explicitly forbid negative energy states in all contexts. The Casimir effect proves that virtual particles in quantum field theory can temporarily have negative energy. The question is whether these fleeting quantum fluctuations could somehow be stabilized or amplified into the macroscopic negative energy densities required for a warp drive. This is where theoretical physics gets truly speculative. We're pushing at the boundaries of knowledge, exploring ideas that might be impossible but aren't obviously impossible. It's uncomfortable territory. Scientists like definitive answers. Yes or no, possible or impossible. But sometimes the honest answer is we don't know yet, and that's where we find ourselves with exotic matter. The Alcubierre Drive forces us to confront the limits of our knowledge. Energy requirements that seemed impossible were reduced through clever geometry. Maybe exotic matter is the next barrier waiting to fall. Or maybe it's the final, insurmountable wall that proves faster-than-light travel is genuinely impossible. Time and research will tell. One thing is certain though, even if the Alcubierre Drive never works, exploring it has already taught us valuable lessons about general relativity, energy conditions, and the flexibility of space-time. That knowledge has value regardless of whether we ever build a working warp engine. Science progresses through ambitious failures as much as triumphant successes. The energy and matter requirements stand as the first major obstacles to realizing Alcubierre's dream. They're formidable, perhaps insurmountable. But they're not the only problems we face. Even if we somehow solved the exotic matter issue and found a way to harness 3 solar masses of energy, other challenges await. Challenges that might be even more fundamental and difficult to overcome. Are you ready to go deeper? Part 3. Control and communication problems. Problem 3. The horizon problem, loss of control. Imagine you've somehow solved the exotic matter problem. You've gathered 3 solar masses of energy. You've engineered structures at the Planck scale. Against all odds, you've created a functioning warp bubble around your spacecraft. You're sitting inside, ready to engage the drive and zoom off to Alpha Centauri. There's just one small problem. You have absolutely no way to control, steer, or stop the vessel. This revelation came from physicist Sergei Korsakoff shortly after Alcubierre's original paper. The problem is rooted in something called the light cone structure of spacetime. In relativity, there's a fundamental limit to what you can affect. An observer at any given moment can only influence points within their future light cone. The region of spacetime that light from their location could reach. Here's the issue. The front of the warp bubble is outside the future light cone of anyone inside the bubble. Any signal you send, any energy field you create, any control mechanism you activate inside the bubble simply cannot reach the front part. It's not a matter of having a weak signal or needing better technology. It's fundamentally impossible based on the structure of spacetime itself. What happens when you try to send a signal forward? Let's say you fire a laser toward the front of the bubble, hoping to interact with the warp field there. The photons from your laser would approach the front of the bubble, but never quite reach it. They'd pile up, accumulating in a layer, always remaining at rest relative to the motion, but never actually arriving at their destination. It's like trying to run on a treadmill that's moving backward faster than you can run forward. This situation is directly analogous to the event horizon of a black hole. Once you cross a black hole's event horizon, there is no way to interact with the universe outside. No signal you send, no light you emit, nothing can escape back across that boundary. The warp bubble creates a similar horizon problem, except it's not about getting out. It's about reaching forward to the part of the bubble that needs to exist for the bubble to function. Think about what this means. The consequences are profound and deeply troubling for anyone hoping to build a warp drive. Anyone or anything inside the bubble cannot control the bubble. They can't steer it. They can't speed it up or slow it down. They can't stop it. They're passengers in the truest sense, along for a ride they have no control over. But it gets worse, much worse. The paradox of warp bubble creation. If the occupants of a warp bubble can't interact with the front of the bubble, then they can't create the bubble in the first place. Think about this carefully. To generate a warp field, you need to emit energy or manipulate matter in a specific configuration around the ship. But any energy field generated from inside the protective central region cannot reach the front section where it needs to be. The bubble needs to surround you, which means part of it must be ahead of you. But you can't affect what's ahead of you because of the light cone limitation. It's a catch-22 situation, a logical impossibility built into the very geometry of the solution. You'd need the bubble to exist before you create it, which is obviously paradoxical. This isn't a minor technical hurdle. This is a fundamental problem with the concept of a self-contained faster-than-light vessel. The Alcubierre Drive, as originally conceived and as most people imagine it, simply cannot be created by the ship that's supposed to use it. The horizon problem kills the idea of a starship enterprise that engages its warp drive whenever Captain Picard orders engage. Does this mean the Alcubierre Drive is completely dead? Not quite, but it forces us to radically reimagine what such a system would look like. The drive cannot be a self-contained entity. You can't just build a ship, install a warp drive, and fly off into the galaxy. The infrastructure requirements become far more demanding. What would be required instead? You'd need pre-existing infrastructure built ahead of time. Imagine an interstellar highway system, a massive tube of structured spacetime stretching between stars. Along this tube, you'd have negative energy field generators positioned at regular intervals, like streetlights along a road. These generators would need to activate in a precisely choreographed sequence as your ship passes. Creating the warp bubble externally, the ship itself wouldn't generate the warp field. The infrastructure would. The ship would simply ride the wave created by this enormous external system. It's less like a car with an engine and more like a train on tracks. Or perhaps more accurately, like a surfer riding a wave they didn't create. Could humanity ever build something like this? We're talking about engineering on a scale that dwarfs anything we've ever attempted. The Large Hadron Collider, our most ambitious particle physics experiment, is 17 miles in circumference. Now imagine building a similar system stretching across light years, trillions upon trillions of miles. The construction timeline would span millennia. The resource requirements would consume the output of entire solar systems. Yet from a purely physics standpoint, there's no law that forbids it. It's an engineering problem rather than a fundamental impossibility. Just an engineering problem of such staggering scope that calling it ambitious would be a laughable understatement. But engineering problems, no matter how difficult, are potentially solvable given enough time, resources, and determination. Would you devote your civilization's entire productive capacity for thousands of years to build a single interstellar highway? That's the kind of commitment we're talking about here. The horizon problem doesn't make warp drives impossible, but it makes them require infrastructure that seems beyond any reasonable expectation. Problem 4. External radiation danger. The horizon problem creates another issue, one that's more immediately dangerous than simple lack of control. This problem was explored in a recent paper by McMoneagle and colleagues, and it paints a rather apocalyptic picture of what happens when a warp bubble arrives at its destination. Imagine a photon traveling peacefully through space, minding its own business. Suddenly, from behind, a faster-than-light warp bubble catches up to it. Like a snowplow moving down a street, the bubble scoops up the photon and drags it along at superluminal speeds. The photon gets trapped in the front edge of the bubble, unable to escape forward or backward. This doesn't just happen to one photon. It happens to every particle the bubble encounters along its path. Photons, cosmic rays, hydrogen atoms, dust particles, everything gets swept up and accumulated in the front of the bubble. They're all dragged along, compressed and concentrated in that forward region. Now here's where it gets interesting in a terrifying way. What happens when the warp bubble finally stops at its destination? All those particles that got scooped up suddenly get released, and they don't just drift away gently. They get released with enormous energy, far more than they originally had, thanks to the bubble's motion. The energy dump is catastrophic. McMoneagle's calculations show it's sufficient to completely obliterate entire planets. Not damage them, not cause extinctions, obliterate them, reduce them to vapor and debris. This is probably not how Captain Picard imagined arriving for diplomatic peace negotiations. Picture the scenario. You've built your interstellar highway. You've invested millennia of effort and the resources of your entire civilization. You send your first ship to a neighboring star system, perhaps one with a habitable planet you hope to establish contact with. The ship works perfectly, crossing light years in mere days. And when it arrives, it sterilizes the entire system with a burst of radiation that makes a supernova look gentle by comparison. Fortunately, there's a relatively simple solution to this particular problem. You don't stop the warp bubble directly at your destination. Instead, you stop it outside the target system, perhaps a few light days away, and then continue the rest of your journey at normal subliminal speeds. The deadly particle release happens in empty space where it can't hurt anything. This mitigation strategy works, but it does reduce the practical utility of the warp drive somewhat. You can't make quick trips to planetary surfaces. You can't zip directly into orbit around your target. You need to build in deceleration zones, safe distances where the radiation burst won't cause harm. It's a manageable problem, but one more complication in an already impossibly complicated system. Still, this external radiation danger hardly prohibits the warp drive as a concept. It's more of a safety consideration, a hazard to be aware of and planned around. Dangerous, yes, but not fundamentally impossible to deal with. Unfortunately, there's another radiation problem that's far more serious and far less easy to solve. Internal radiation, the Hawking radiation problem. Remember how the warp bubble creates a horizon similar to a black hole's event horizon? Well, that similarity isn't just metaphorical. It has real physical consequences, and those consequences are absolutely devastating. Wherever you have a horizon in general relativity, you get something called Hawking radiation. This is a quantum effect discovered by Stephen Hawking in the 1970s. Near any horizon, quantum mechanics causes particle and antiparticle pairs to spontaneously pop into existence from the vacuum. Normally, these pairs immediately annihilate each other, but near a horizon, something different happens. One particle falls across the horizon while its partner escapes. From an outside observer's perspective, the horizon appears to be radiating particles. This is Hawking radiation, and it's not just theoretical. We have strong indirect evidence that it occurs around black holes, though we've never observed it directly because it's so incredibly faint for astronomical-sized black holes. But the warp bubble isn't astronomical in size. Remember that ultra-thin shell we talked about, approaching the Planck length in width? That tiny scale creates problems. Lots of problems. Physicist Fanazzi and colleagues investigated this issue in 2009. They showed that Hawking radiation will be generated along the rim of the warp bubble due to quantum pair production effects. The radiation will have a thermal temperature determined by the surface gravity of the warp bubble shell, and because that shell is so incredibly thin, approaching the Planck length, the surface gravity is enormous. How enormous? The thermal radiation hits temperatures on the order of the Planck temperature. That's approximately 10 to the power of 32 degrees Kelvin. In scientific notation, that's 10 to the 32nd power Kelvin. It's the highest temperature that has any physical meaning in our current understanding of physics. It's the temperature that existed in the first moments after the Big Bang, when the entire universe was an unimaginably hot, dense soup of energy. Now imagine that temperature focused on your spacecraft and crew. The thermal flux would instantly vaporize anything and everything. Not just kill the crew, not just destroy the ship, completely convert everything into a plasma of fundamental particles. The atoms themselves would be torn apart by the sheer energy density. Fanazzi's conclusion was stark and unambiguous. This radiation leads to a completely unstable system. The warp bubble would almost immediately collapse as soon as it formed, destroyed by its own Hawking radiation before it could even begin accelerating. It's a fundamental instability built into the geometry of the solution. This is a severe problem, perhaps the most severe we've encountered so far. The exotic matter issue might be solved if we discover new physics. The energy requirements might be reduced with clever geometry modifications. The horizon control problem might be bypassed with external infrastructure. But the Hawking radiation problem seems deeply fundamental. Is there any hope? The only possibility anyone can see is finding an alternative warp bubble metric, a different geometric configuration that somehow reduces the Hawking temperature dramatically. Maybe a thicker shell, though that creates its own problems. Maybe a different shape entirely. Maybe some quantum effect we haven't discovered yet that suppresses the radiation. But as of now, we don't have such a solution. The Hawking radiation problem stands as a potentially insurmountable barrier, a fundamental consequence of combining quantum mechanics with the extreme geometries required for warp travel. It suggests that even if everything else worked perfectly, the warp bubble would destroy itself before it could function. Comparing obstacles, engineering versus physics, let's take stock of where we are. We've now examined 4 major problems with the Alcubierre Drive. 2 of them, the energy requirements and the horizon problem, might generously be classified as engineering challenges. Incredibly difficult engineering challenges, to be sure, requiring technology far beyond anything we can currently imagine. But physics doesn't explicitly forbid solving them. The other 2 problems are more fundamental. The exotic matter requirement challenges our understanding of what kinds of matter and energy can exist in our universe. The Hawking radiation problem suggests that the warp bubble geometry itself is inherently unstable in ways that might be impossible to fix. There's a crucial difference between these categories. Engineering problems are hard but potentially solvable given enough time, intelligence, and resources. Human history is full of engineering problems that seemed impossible until someone solved them. Heavier than air flight, nuclear energy, quantum computers, the list goes on. Fundamental physics problems are different. If the universe simply doesn't allow negative mass to exist, then no amount of clever engineering will create it. If the Hawking radiation instability is intrinsic to the geometry, then no material or technology can prevent it. Physics problems require new physics, new understanding, perhaps even a revolution in how we think about reality. Which category do these problems really fall into? That's the trillion-dollar question, and honestly, we don't know for certain. What seems fundamental today sometimes turns out to be merely very hard tomorrow. The boundary between impossible and just extremely difficult is fuzzy and shifts as our knowledge grows. Consider the energy requirements. Reducing them from 10 universes to 3 solar masses seemed to shift the problem from absolutely impossible to theoretically possible with advanced technology. Could further geometric refinements reduce it to 1 solar mass, to Jupiter's mass, to something achievable with fusion power? Each step makes it less of a physics problem and more of an engineering problem. Or consider the Hawking radiation issue. Our current understanding suggests it's fundamental and unavoidable. But our current understanding is based on semi-classical quantum gravity, an approximation that we know breaks down at the Planck scale. A true theory of quantum gravity might reveal new effects that suppress or eliminate the radiation. We simply don't know because we don't have that theory yet. What's your intuition about this boundary between hard and impossible? Do you think these are engineering challenges waiting for sufficiently advanced technology, or fundamental barriers that no amount of progress can overcome? The answer might determine whether faster-than-light travel remains science fiction forever or becomes science fact in some distant future. The problems we've examined so far are formidable, but they're not the only obstacles standing in our way. There are deeper issues yet to explore, problems that strike at the very heart of what's possible within the laws of physics. The next challenges we'll face make the energy requirements and radiation problems look almost simple by comparison. Ready to go even deeper into the rabbit hole? Part 4. The chicken and egg paradox and FTL impossibility. Problem 5. The catch-22 situation. We're about to encounter what might be the most philosophically frustrating obstacle yet. It's a problem that makes you want to throw your hands up in despair because of its sheer logical circularity. Several physicists have argued that there's a fatal flaw in the entire concept of a superluminal warp drive, and that flaw is this: you need a warp drive to make a warp drive. Let that sink in for a moment. It's a perfect catch-22, a snake eating its own tail, a paradox wrapped in an enigma. The argument goes like this. The Alcubierre metric describes a warping of space-time, a geometric distortion represented mathematically, but achieving that warp bubble geometry doesn't automatically give you a faster-than-light warp drive. There's a crucial missing step. In 1998, physicist Cole made a compelling argument. For the space-time geometry to be moving superluminally, the matter distribution that creates it must also be moving faster than light. This isn't optional. It's a requirement that follows directly from how general relativity works. The geometry doesn't just float around independently. It's caused by matter and energy, and if that geometry is moving faster than light, then at least some of the matter creating it must also be moving faster than light. This conclusion was later supported and clarified by Chris van den Broek, who stated that at least some of the exotic matter must be moving at superluminal speeds. Not all of it necessarily, but enough of it to create and maintain the faster-than-light motion of the bubble itself. And here's where the problem becomes insurmountable. Remember the structure of the warp bubble. There's an inner region of flat space-time where passengers sit, protected from the extreme conditions outside. To warp space-time around this inner region while keeping it flat inside, you need the exotic matter to be positioned outside that protected zone. The exotic matter can't all be sitting comfortably inside where it's safe. It has to be out there in the shell, in the region where space-time is being bent and stretched. But matter outside that inner protected region is subject to the normal laws of physics. And one of those laws is that nothing with mass can move faster than light. It's not just difficult. It's prohibited by special relativity, one of the most thoroughly tested theories in all of physics. Every experiment we've ever done confirms it. Accelerate something with mass toward light speed, and it requires exponentially more energy. Reach light speed? Impossible. Exceed it? Not going to happen. So we're stuck. The exotic matter needs to be moving faster than light to create a faster than light warp bubble, but the exotic matter can't be entirely inside the protected region, and anything outside that region can't move faster than light. It's a logical impossibility, a fundamental contradiction built into the concept itself. What does this mean practically? If you somehow did manage to create a warp bubble moving at superluminal speeds, the outer shell of exotic matter would immediately be left behind. It can't keep up because physics won't let it, and once that shell is left behind, the carefully engineered space-time geometry collapses. The warp effect disappears. The bubble pops like a soap bubble touched by a needle. Cole seemed genuinely surprised that Alcubierre was unaware of this issue in his original paper. Van den Broek went even further, stating rather bluntly that the Alcubierre spacetime is an example of what can happen when Einstein's equations are run in the wrong direction. It's mathematically valid, but physically unrealizable, like calculating the square root of -1. The math works, but it doesn't correspond to anything in physical reality. Does this kill the dream completely? Not quite, but the escape routes are narrow and unsatisfying. Van den Broek's speculative solution. Van den Broek, despite his criticism, did offer one speculative possibility for getting around this problem. What if the distribution of exotic matter could expand and fan out into a tail at the back of the bubble? Imagine a contrail, like the vapor trail left by a jet airplane, except made of exotic matter. The idea would be that as the bubble moves forward, it continuously sheds exotic matter behind it, creating an expanding wake. This matter wouldn't need to keep up with the bubble because it would be left behind intentionally. The bubble would consume exotic matter from the front and deposit it at the rear, maintaining the necessary configuration to sustain the warp effect without requiring all the exotic matter to travel superluminally. It's a creative solution, but Van den Broek himself admits it's unclear whether this is even possible. The physics of such a configuration are murky at best. How would you create this continuous stream of exotic matter? Where would it come from? How would you ensure it gets deposited in exactly the right configuration behind the bubble? These questions don't have answers. Moreover, this solution still requires exotic matter to exist in the first place. Which brings us back to the negative energy problem we discussed earlier, and it would require enormous quantities of exotic matter constantly being consumed and deposited. The resource requirements might be even more absurd than the already absurd energy requirements we've talked about. Think about crossing just 1 light year with this system. You'd need to lay down a light-year-long trail of exotic matter behind you. Even if exotic matter existed, and even if you could manipulate it, the sheer quantity needed makes the proposal seem fantastical. It's not solving the problem so much as replacing one impossible requirement with a different impossible requirement. Still, it represents a potential loophole, however narrow and speculative. Maybe there's something we're missing about exotic matter behavior. Maybe there are configurations or quantum effects we haven't considered. The history of physics is full of problems that seemed impossible until someone found a clever workaround. Could this be another case where ingenuity triumphs over apparent impossibility? Or are we just refusing to accept the obvious conclusion that faster-than-light travel is fundamentally prohibited by the structure of reality itself? Bobrick and Martyrs, 2021 analysis. The most recent and perhaps most damning analysis of this problem came in 2021 from physicists Bobrick and Martyrs. They took a systematic look at the warp drive literature and identified a pattern. The overwhelming majority of papers and proposals assume that the required space-time curvature is already moving superluminally. They start with that assumption and work forward from there. But this assumption is problematic. How did that curvature get to be moving faster than light in the first place? Space-time curvature doesn't just spontaneously decide to move. It's caused by distributions of matter and energy. And if that curvature is moving superluminally, then the matter and energy causing it must have been moving superluminally too. Which brings us right back to the catch-22. Bobrick made his position crystal clear in a 2021 interview with Scientific American. He stated unequivocally that none of the physically conceivable warp drives can accelerate to speeds faster than light. Not, it's really hard. Not, we need better technology. Simply, they cannot do it. The physics prohibits it fundamentally. This isn't a fringe opinion from a contrarian trying to make a name for himself. Bobrick and Martyrs' analysis is rigorous, mathematically sophisticated, and addresses the core logical structure of warp drive proposals. Their argument isn't about energy requirements or exotic matter. It's more fundamental than that. It's about the logical consistency of the entire concept. When you trace through the causality carefully, keeping track of what needs to cause what, the circular logic becomes apparent. The warp bubble needs superluminal motion to be useful. That motion requires superluminal matter distributions. But creating those distributions would itself require a warp drive. It's turtles all the way down, an infinite regress with no foundation. The scientific community hasn't universally accepted this conclusion. There are still papers being written, proposals being made, arguments being advanced. But the catch-22 problem is gaining recognition as a serious, possibly fatal flaw in the entire faster-than-light warp drive concept. It's not an engineering challenge. It's a logical impossibility. How do you feel about this? Disappointed? Frustrated? Or perhaps relieved that the universe maintains some logical consistency after all? The implications are profound either way. Saving the concept. Subliminal warp drives. Is there a way to save the Alcubierre Drive from this chicken and egg problem? Actually, yes. There's one obvious solution, though it requires surrendering the most exciting aspect of the concept. We give up on faster-than-light travel and settle for subliminal warp drives instead. If the warp bubble moves slower than light, the catch-22 disappears completely. We can already accelerate objects to any speed below light speed. It's hard, sure. It requires enormous energy for speeds approaching light speed. But it's not prohibited. There's no fundamental barrier. Particle accelerators routinely push particles to 99.9% of light speed. With enough energy, we could go even closer to light speed, though never quite reaching it. A subliminal warp drive would still be revolutionary. Even moving at 99% of light speed, you could cross to our nearest stellar neighbor, Alpha Centauri, in about 4.5 years. That's within a human lifetime. A crew could make the journey, explore, and return home while friends and family were still alive. It's not the instantaneous travel of science fiction, but it's vastly better than the centuries or millennia that conventional rockets would require. Moreover, subliminal warp drives would still offer unique advantages over conventional propulsion. Inside the bubble, time would pass normally for the passengers. They wouldn't experience the time dilation effects that come with near light speed travel. The twin paradox wouldn't apply. You could synchronize with people back on Earth, maintaining communication and coordination across interstellar distances. The energy requirements might also be more manageable. The closer you try to get to light speed with conventional propulsion, the more energy you need, approaching infinity as you approach light speed. But a warp drive warps space itself. The energy requirements don't necessarily follow the same curve. There might be a sweet spot where you get useful, significant fractions of light speed without the impossible energy demands of faster-than-light travel. Would you accept subliminal warp travel as a compromise? It's not as romantic as zooming across the galaxy at warp 9, but it's still extraordinary compared to what we have now. Sometimes the practical, achievable goal is better than the impossible dream. Sometimes accepting limitations opens up possibilities that rigid insistence on the impossible closes off. But there's another approach to saving the concept, one that doesn't require giving up on faster-than-light travel. Alternative architectures, tubes and wormholes. If the catch-22 problem kills self-contained faster-than-light warp drives, maybe the solution is to abandon the idea of self-contained ships altogether. Several alternatives exist that sidestep the problem by changing the fundamental architecture. Sergei Krosakov, the same physicist who identified the horizon problem, proposed a continuous tube of warped spacetime. Instead of a bubble surrounding a single ship, Imagine a tunnel connecting to star systems. The entire tunnel exists in a warped state, with exotic matter distributed throughout its structure. Ships travel through this tunnel, but they're not creating the warp effect themselves. The infrastructure creates it. This avoids the catch-22 because the infrastructure is static, or at least can be built up gradually over time. You don't need the tunnel to be moving faster than light. You just need it to exist as a shortcut through space-time. Ships moving through the tunnel at normal speeds would effectively travel faster than light relative to the outside universe. Not because they're moving superluminally, but because they're taking a shorter path. It's similar to how highways work on Earth. A highway doesn't move. It's infrastructure, built once and then used repeatedly. Cars on the highway aren't doing anything special. They're just driving at normal speeds on a route that's more efficient than the alternatives. A space-time tunnel would function the same way, except the efficiency comes from warping the geometry of space itself, rather than just paving a smooth road. Then there are Einstein-Rosen bridges, more commonly known as wormholes. These are solutions to Einstein's equations that connect to distant points in space-time through a tunnel or throat. Travel through the wormhole would be faster than going around through normal space, effectively allowing faster than light travel without actually moving faster than light. Wormholes have their own problems, of course. They require exotic matter to stay open. The throat tends to collapse unless held open by negative energy densities. The stability issues are severe, but conceptually, they avoid the catch-22 problem because they're not self-propelled vessels. Their topology, geometric features of space-time itself. Both of these alternatives represent fundamental shifts in how we think about interstellar travel. Instead of building ships, we'd be building infrastructure. Instead of vehicles, we'd be constructing space-time itself into useful configurations. The engineering challenges are staggering, probably even more extreme than building a self-contained warp drive. But at least they're not logically impossible. The shift from ships to infrastructure also changes the economics and sociology of interstellar travel. It becomes a civilizational project rather than an individual or corporate venture. You don't just build a starship and fly off. You invest centuries or millennia building the infrastructure, and then anyone can use it. It's more like building the Roman road system than building a car. Is that vision more or less appealing than the Star Trek model of independent starships? There's no right answer. They're different paradigms with different implications for how spacefaring civilization would develop. Both face enormous challenges. Both require breakthroughs we haven't achieved. But one is logically consistent while the other appears to be fundamentally paradoxical. Current understanding, the verdict on self-contained F. Let's synthesize where the physics community currently stands on this issue. The consensus, though not universal, is increasingly skeptical about self-contained faster-than-light warp drives. The catch-22 problem appears to be fundamental, not merely a technical difficulty waiting for a clever solution. The logic is straightforward and hard to refute. Creating a superluminal warp bubble requires superluminal matter distributions. Creating superluminal matter distributions is prohibited by relativity for anything outside the protected inner region. Therefore, self-contained superluminal warp bubbles cannot be created. It's a simple syllogism with premises that are hard to deny and a conclusion that follows inevitably. Does this mean Alcubierre's work was pointless? Absolutely not. Even if faster-than-light warp drives are impossible, the exploration of the concept has taught us enormous amounts about general relativity, space-time geometry, energy conditions, and the limits of what's possible within known physics. Sometimes the value of an idea lies not in its practical realization, but in what we learn by seriously examining it. Moreover, the door remains open for subliminal warp drives and for infrastructure-based approaches like space-time tunnels or wormhole. These concepts face their own severe challenges, but they're not obviously paradoxical in the way that self-contained faster-than-light ships appear to be. The dream of practical interstellar travel isn't dead. It's just evolving into different forms. The Catch-22 problem also reveals something profound about the structure of physical law. The universe seems to have consistency checks built into it, logical constraints that prevent paradoxes and contradictions. Faster-than-light travel isn't prohibited by a simple rule. It's prohibited by the self-consistent logic of space-time itself. The laws of physics interlock in ways that prevent certain configurations from existing, even when the mathematics seems to allow them. There's a beauty in that, a deep elegance. The universe makes sense. It hangs together logically. Even when that logic denies us something we desperately want, there's satisfaction in understanding why. We're not being arbitrarily forbidden from faster-than-light travel by some cosmic killjoy. We're being shown that certain concepts are internally contradictory, impossible in the same way that square circles are impossible. Where does your intuition lead you on this? Do you accept the logical argument that self-contained faster-than-light warp drives are fundamentally impossible? Or do you hold out hope that some undiscovered principle of physics will provide a way around the Catch-22? The answer might say as much about your philosophy as it does about physics. We're not done yet, though. There's one more problem to discuss, and it might be the most disturbing of all, because even if we could somehow solve all these issues, even if exotic matter exists and the Catch-22 has a solution we haven't found yet, there's still the matter of what faster-than-light travel does to causality itself. Prepare yourself. Things are about to get weird. Part 5, Time Travel and Final Conclusions. Problem 6, Causality Violations and Closed Time-like Curves. We've arrived at the final major problem with the Alcubierre Drive, and it might be the most philosophically disturbing one of all. Even if you solve every other issue we've discussed, there's still one unavoidable consequence of faster-than-light travel. It allows backwards time travel. This isn't speculation. It's a proven mathematical consequence of combining faster-than-light travel with relativity. The warp drive can create what physicists call closed time-like curves, or CTCs. These are paths through space-time that loop back on themselves, allowing you to return to a point in your own past. The most famous example is the grandfather paradox. Imagine using your warp drive to go back in time and prevent your grandfather from meeting your grandmother. If you succeed, you're never born. But if you're never born, you can't go back in time. The logic eats itself, creating an impossible contradiction. These paradoxes represent a fundamental breakdown in the predictive power of physics. If you can create paradoxes, then the future isn't determined by the past in any consistent way. The entire framework of cause and effect collapses. General relativity does not forbid backwards time travel, but the consequences make many physicists deeply uncomfortable. Stephen Hawking was so troubled that he proposed the chronology protection conjecture. Hawking suggested that whenever someone attempts to create a time machine, quantum effects would automatically prevent it from working. Hawking's argument involves feedback, similar to what happens when you put a microphone too close to a speaker. The sound loops, increasing exponentially in intensity until something breaks. A time machine would create similar feedback loops. Particles or information could loop through time repeatedly, their effects compounding until they destroy the time machine before it can function. It's elegant, and there's serious mathematical work supporting it. But it remains unproven. Until we have a complete theory of quantum gravity, we can't be certain the universe protects itself from time travel paradoxes. How warp drives lead to time travel. You might be wondering how faster than light travel leads to time travel. It seems counterintuitive. The relationship is ironclad in relativity, both special and general. This isn't time dilation where moving fast makes your clock run slow. The passengers in an Alcubierre bubble are at rest in their own reference frame. The time travel effect comes from something more fundamental about space-time structure itself. The core insight is this: in relativity, faster than light travel in space is mathematically equivalent to backwards travel in time. They're the same thing viewed from different perspectives. If you can go faster than light, you can reach your own past. It's a package deal. This was proven for the Alcubierre Drive by physicist Alan Everett in 1996. Everett showed that closed time-like curves appear in general relativity with superluminal warp bubbles. The conclusion is inescapable. Alcubierre himself acknowledges this completely. In interviews, he's been explicit about the time travel implications. He stated clearly that there's a general proof that any method allowing faster than light travel can in principle be turned into a time machine. His 2017 follow-up paper included a derivation explicitly demonstrating this point. The evidence is overwhelming. Closed time-like curves appear to be an inherent, fundamental feature of faster-than-light travel. There's no way around it within our current understanding of physics. Hawking's chronology, protection, and possible escape routes. If the Alcubierre Drive inevitably allows time travel, then the question becomes whether the universe permits time travel at all. If Hawking's chronology protection conjecture is correct, then time machines are automatically impossible, which would mean faster-than-light warp drives are also impossible. When you try to create closed time-like curves, quantum fluctuations would be amplified enormously. Virtual particles could travel through the curve multiple times. The probability amplitudes would add up coherently, growing exponentially with each loop. The result would be massive energy density concentrated where the closed time-like curve forms. The time machine would destroy itself before it could function. This argument has detailed calculations supporting it, though they rely on approximations. The calculations suggest chronology protection is real, that the universe genuinely prevents time travel paradoxes, but we can't be absolutely certain without a complete theory of quantum gravity. Are there any escape routes? One option is that our understanding of causality in quantum mechanics might be incomplete. In the many worlds interpretation, when you go back in time and change something, you create a branching timeline. No paradox, no logical contradiction. If many worlds is correct, closed time-like curves don't create contradictions, they create branching realities. Of course, many worlds is controversial and unproven. Using it as foundation is building a hypothesis on top of another hypothesis. But it represents a potential escape route if future physics validates that interpretation. Alcubierre himself suggests the warp drive might still be possible if you simply don't use it as a time machine. Perhaps chronology protection only activates when you actually try to create a paradox. Maybe you could use the warp drive for ordinary faster-than-light travel without triggering destructive quantum effects. Practically, though, it's hard to imagine how this would work. If the capability exists, someone would eventually try to use it. And once anyone creates a closed time-like curve, even accidentally, the quantum feedback would begin. What's your gut feeling here? Does the universe permit time travel paradoxes, or does it have built-in safeguards that prevent them? general conclusions, and overall assessment. Let's survey the complete landscape. We've examined 6 major problems with the Alcubierre Drive. Energy requirements that were initially absurd but got reduced through clever geometry. Exotic matter requirements that might violate fundamental energy conditions. Horizon problems, preventing control and requiring external infrastructure. Radiation problems that could vaporize planets and crews. Catch-22 paradoxes, suggesting self-contained faster-than-light vessels are logically impossible. And causality violations creating time travel paradoxes. Some problems might be solvable. Energy requirements came down dramatically through theoretical refinements. The horizon problem could potentially be addressed through infrastructure-based approaches. The external radiation danger has straightforward mitigation strategies. But other problems appear more fundamental. The exotic matter requirement challenges basic energy conditions. Hawking radiation might make any warp bubble inherently unstable. The Catch-22 problem suggests faster-than-light warp travel requires already having faster-than-light capabilities. And causality violations create paradoxes that threaten logical consistency. Interestingly, almost all these problems disappear if we give up faster-than-light travel and settle for subliminal warp drives. A warp bubble moving at 99% of light speed wouldn't violate causality. It wouldn't require exotic matter to move faster than light. The energy requirements might be more manageable. A subliminal warp drive would still be revolutionary for interstellar travel. You could reach nearby stars in years rather than centuries. You could avoid time dilation effects that plague near light speed conventional travel. It would make practical interstellar exploration feasible within human lifetimes. But for faster-than-light capability, the outlook is grim. The convergence of multiple severe problems suggests the universe doesn't permit superluminal travel. Not through any single prohibition, but through a web of interconnected constraints that collectively make it impossible. What do you take away from this analysis? Disappointment that faster-than-light travel seems impossible. Fascination with the deep interconnections between physical principles. Appreciation for how the universe maintains logical consistency. Inspiration, legacy, and the reality of interstellar travel. Despite the formidable obstacles, the Alcubierre Drive serves a valuable purpose beyond practical feasibility. It inspires. Many scientists became physicists after reading about the warp drive. Seeing energy requirements drop from 10 universes to 3 solar masses showed what human ingenuity could accomplish. The decades of papers following Alcubierre's work represent an intellectual playground where physicists explore the limits of general relativity. Each paper advances our understanding of energy conditions, horizon structures, quantum effects, incurved space-time, and causality. This knowledge has value independent of whether we build a warp drive. Science progresses through bold speculation as much as careful measurement. The Alcubierre Drive stands as one of the most audacious ideas in modern physics. It took a staple of science fiction and asked seriously whether real physics could accommodate it. The answer appears to be probably not. But the journey taught us profound truths about space-time, energy, matter, and causality. Here's something important. The impossibility of faster-than-light warp drives doesn't make interstellar travel impossible. It just means we need to do it the slow way. Even with improved conventional rockets, we could reach nearby stars within human lifetimes using significant fractions of light speed. Generation ships could reach more distant targets. Suspended animation could let crews sleep through the journey. Digital consciousness uploaded to computers could travel as information. Time dilation from near light speed travel could actually be an advantage. A crew traveling at 99.9% of light speed would experience time passing much more slowly. A journey that takes decades for Earth could be mere months for the crew. Patience is another option. Von Neumann probes, self-replicating machines that travel slowly between stars, could colonize the galaxy over millions of years. Evolution itself is patient on geological timescales. Perhaps civilization can be equally patient. Interstellar travel doesn't require warp drives. It requires commitment, resources, and time. If we accept that limit, the stars are still reachable. Not through shortcuts, but through methodical expansion that works within the rules. Final reflections, dreams, limits, and progress. The Alcubierre Drive represents something profound about human nature. We see a limit and immediately think about how to get around it. The universe says nothing can travel faster than light. We respond by asking, what if we move space itself? But ultimately, physics might be telling us this loophole doesn't exist. Not because of any single barrier, but because of multiple problems that collectively make faster than light travel impossible. The energy requirements, exotic matter, control issues, radiation, logical paradoxes, causality violations. Together, they form a wall that might be truly unbreakable. Yet we should keep looking. History shows that declared impossibilities sometimes fall to new understanding. Maybe someday someone will find the key that makes warp drives work. Maybe there's a revolution in physics waiting to be discovered. More likely though, the speed of light will stand as an absolute limit. Faster than light travel would break causality, allow time travel paradoxes, create logical contradictions the universe doesn't permit. The light speed limit isn't arbitrary. It's the speed at which cause and effect propagate through space-time. There's beauty in that limitation. The universe makes sense. It has rules, and those rules create a coherent, self-consistent whole. Physics works because the universe is lawful. Predictions are possible because the future follows from the past in consistent ways. Perhaps the lesson isn't that we should keep trying to build one. Perhaps it's that we should appreciate the elegant structure of physical law. Perhaps we should redirect creative energy toward achievable goals within the rules, toward subliminal interstellar travel, toward understanding the universe as it is. Or perhaps we should keep dreaming anyway, keep pushing at boundaries, keep looking for loopholes, even if they probably don't exist. Because sometimes the journey matters more than the destination. Sometimes exploring an impossibility teaches us truths we wouldn't learn otherwise. The Alcubierre Drive will be remembered not as a practical spaceship design, but as one of the boldest intellectual adventures in modern physics, a serious, scientific exploration of whether faster-than-light travel could exist within real physics. The answer appears to be no, but the question was worth asking. Stay curious, stay thoughtful, keep questioning the limits of what's possible. Sometimes you'll find they're not as hard as they seemed. Other times you'll discover they're absolute. Either way, you'll have learned something profound about the universe we inhabit and our place within it. The stars are waiting. Whether we reach them fast or slow, the journey will teach us who we are and what we can become.